Welcome back to the deep dive. Today, we're plunging into a paper that tackles one of the most pressing, maybe even frustrating challenges in the world of large language models: efficient fine-tuning. As LLMs keep getting bigger and spreading through the open source communities, trying to adapt these, well, colossal models for specific tasks with limited compute, it's gotten incredibly complex. Sometimes feels like you need a supercomputer just to even get started. We're talking about LlamaFactory, unified efficient fine-tuning of 100+ language models. It's a framework designed not just to streamline, but really to democratize this whole critical process. And it's already made a massive splash. I mean, what, over 25,000 stars, 3,000 forks on GitHub? That's serious traction. For those of you deep in machine learning, data science, advanced math, that bridging that gap, the gap between cutting-edge research and something practical, something accessible, well, that's a huge achievement, especially with the scale and complexity we're dealing with now.
Indeed. And just think about the sheer pain point LlamaFactory addresses here. I mean, before this, if you wanted to try out, say, QLoRa on a Mistral model for your specific task, and then maybe you wanted to switch gears, try a Galore approach on a, I don't know, a Gemma model,
Yeah.
you'd be diving into totally different code bases.
Oh, yeah. Wrestling with compatibility.
Exactly. Wrestling with compatibility issues, potentially spending weeks just setting things up, implementing it all before you even start your actual fine-tuning experiment. LlamaFactory basically unifies all of that. It's kind of like having a universal adapter, for pretty much every LLM and every efficient fine-tuning method you can think of, and it's all accessible from this single, pretty intuitive dashboard. This just dramatically cuts down the time from having a research idea to actually running a working experiment. And that's truly game-changing. So yeah, we'll explore how this framework empirically backs up its claims on efficiency and effectiveness. It really provides a clear shortcut to getting up to speed on this critical development. Let's unpack it.
Okay, so large language models. As you know, they've fundamentally transformed the whole AI landscape. Their reasoning capabilities are, well, pretty remarkable. They're powering everything now: sophisticated question answering, nuanced machine translation, even precise information extraction. And the open source community, especially platforms like Hugging Face, they now list, over 5,000 models. It's incredible. Offers so much convenience and choice, which is fantastic on the surface.
It is fantastic, but that very abundance, while hugely beneficial, it definitely comes with its own set of pretty significant challenges. The primary hurdle, really, in adapting these LLMs to your specific downstream tasks is just the sheer scale involved.
Yeah.
You're often looking at fine-tuning billions, literally billions of parameters, and usually with constrained computational resources. That's the reality for most people. Now, while the research community has developed various efficient fine-tuning methods over the years, like freeze tuning from Holsby and colleagues, or low-rank adaptation, LoRa, which is super popular now.
Right, and QLoRa.
And its quantized cousin, QLoRa, exactly. The critical gap, though, has been the lack of a systematic, unified framework. We really needed a solution that could consistently apply all these different methods across all these different LLMs, and ideally wrap it all up in a user-friendly interface for seamless customization. That's the chasm LlamaFactory is really trying to bridge.
So this is precisely where LlamaFactory steps in, and not just as another tool, but as you said, like a democratizer for LLM fine-tuning. It unifies this whole variety of efficient methods through scalable modules. The ambition here seems massive. Enable fine-tuning for hundreds of LLMs with minimal resources, high throughput, basically lowering the barrier to entry for advanced model customization for pretty much everyone.
Exactly. And it goes beyond just efficiency in terms of saving GPU memory. The framework also critically streamlines commonly used training approaches, things that are absolutely essential for modern LLM development. So that includes foundational methods like generative pre-training, supervised fine-tuning, SFT, but also the more advanced alignment techniques. Things like reinforcement learning from human feedback, RLHF.
Which is notoriously complex.
Notoriously complex or resource hungry, yeah. And also direct preference optimization, DPO. What's particularly powerful, I think, is its accessibility. Users can use traditional command line interfaces if they want that granular control. Or, maybe more revolutionary, they can use this intuitive web interface called LlamaBoard. This means customization requires minimal coding effort, or in many cases, absolutely no coding effort at all.
Wow.
Yeah. So for practitioners, for researchers who want to focus on the actual experimentation, not wrestling with implementation details, well, this is a genuine game changer.
Okay, so the authors highlight this modular design. 3 main components: model loader, data worker, and trainer. And the philosophy was to minimize dependencies between them, right? To make it scale. Can you elaborate a bit on how that modularity actually helps them support, hundreds of models and data sets? What does that look like in practice?
Yeah, it's a really well thought out, multi-pronged approach. It genuinely reduces the integration cost, the friction. So the model loader first establishes this robust model registry. This lets it precisely attack adapters because it knows how to identify the exact layers needed for different parameter-efficient techniques, like LoRa or DORA.
Okay.
Then the data worker develops this comprehensive data description specification. Think of it like a universal translator for data sets. It allows it to gather and align vastly different data sets, mapping their columns, no matter the original format, alpaca style, shared GPT style, whatever. It aligns them to a standard structure. And finally, the trainer provides these plug-and-play implementations for state-of-the-art fine-tuning methods. You can activate them just by replacing default components. It's designed for easy swapping. This whole design means modules can be reused and combined across all sorts of training approaches without constant re-engineering or headaches. It's a very systematic way to manage all that complexity.
And the underlying infrastructure is obviously just as important. What's LlamaFactory actually built on? How does it leverage the existing open source ecosystem? Because that's key too.
Absolutely.
Yeah.
The implementation details really underscore its robustness and its commitment to the open source community. It's built on PyTorch, which is foundational, of course, and it integrates heavily with leading open source libraries. For model handling, it uses Hugging Face's Transformers library, the standard. For parameter-efficient fine-tuning techniques, it uses PEFT, which is Hugging Face's library specifically for that. And for reinforcement learning, it leverages TRL, the Transformer Reinforcement Learning Library. This deep integration offers a much higher level of abstraction, making these complex operations way more manageable for the user. And LlamaBoard, that no-code web interface we mentioned, that's a testament to this philosophy. It's built using Gradio, which itself simplifies creating machine learning UIs.
Right.
The whole project is open sourced under the Apache 2.0 license, very permissive, and its adoption is already clear. Models like Gemster 7b are built on it. Loads of other research efforts are using the framework. It's definitely cementing its position as a go-to tool in this space.
So when we look at the existing landscape, other LLM adaptation frameworks out there, what specifically makes LlamaFactory stand out? What's its real comparative advantage against things like, say, FastChat or LitGPT?
Yeah, the paper does explicitly compare LlamaFactory with several popular frameworks. You mentioned FastChat, LitGPT. There's also Llama Adapter, OpenInstruct, Colossal AI, LMFlow, GPT-4all, quite a few. What stands out most profoundly, especially if you look at their comparison table, table 1 in the paper, is LlamaFactory's much broader and more comprehensive support. And critically, it supports both a wider range of efficient fine-tuning techniques and a wider array of training approaches.
Okay, so breadth and depth.
It's exactly, breadth and depth. For instance, it uniquely supports methods like DORA, LoRa plus PISA, BATM optimizer, S2 attention for long contexts, and also advanced preference optimization methods like KTO and or RPO. These are really cutting-edge techniques. They're not universally found or sometimes not present at all in the other frameworks they listed. So this comprehensive integration means that a single platform, LlamaFactory, can effectively cater to a much, much wider array of specific fine-tuning needs. Everything from optimizing how parameters are updated to enhancing the actual computational efficiency. It's really designed as an ecosystem for maximum flexibility and power. Makes it a truly unified solution rather than just, a collection of separate tools you still have to somehow stitch together yourself.
Okay, so the paper neatly categorizes these efficient LLM fine-tuning techniques into two main buckets, right? Which helps understand the dual approach they take to reducing resource intensity. It's not just about one thing, but a more holistic view of efficiency. Can you give us a sense of those two categories?
Precisely. Yeah, it's a useful distinction. The first category focuses on efficient optimization techniques. These primarily aim to fine-tune the vast number of parameters in LLMs while minimizing the training costs associated with that. So this focuses on what parameters get updated and how those updates are applied efficiently.
Okay, the what's and how of parameter updates.
Exactly. The second category is efficient computation methods. This focuses more on reducing the time or the memory space required for the actual computations happening within the LLMs. So this addresses the operational efficiency, how the math gets done faster or cheaper.
Got it. Algorithmic versus operational.
You put it that way, yeah. Both are absolutely crucial for practical LLM fine-tuning, especially if you're working on resource-constrained hardware. And LlamaFactory integrates a significant array from both categories, as you can see in their compatibility table. Table 2. This dual approach really ensures that efficiency gains are realized at both the level of the optimization algorithm itself and also at the level of how the hardware is actually utilized.
That makes perfect sense. So we're trying to fine-tune these massive models without, breaking the bank or melting our GPUs. Let's talk about optimizing those billions of parameters first. What are some of the most clever ways LlamaFactory helps us do that? Are there any approaches here that really caught your eye in terms of how they tackle that fundamental challenge?
Absolutely. There are several really neat techniques integrated here, each with its own clever angle on optimizing the parameters. Let's start with QLoRa. It's arguably one of the most impactful recently. It builds directly on LoRa, the technique that introduces small, trainable, low-rank matrices, adapters to specific layers while freezing the bulk of the model.
Right, the parameter-efficient approach.
Exactly. QLoRa takes that a crucial step further. It combines LoRa with quantization. So this means the vast majority of the model, the frozen pre-trained weights, are represented in a lower precision format, typically 4-bit. This drastically, and I mean drastically, cuts down memory usage.
And that's huge for accessibility.
It's monumental. I mean, to put that memory reduction into perspective, achieving these low memory footprints isn't just a minor optimization. It's often the difference between needing, like you said, a whole server rack to fine-tune a model and potentially being able to do it on a single high-end consumer GPU.
Wow.
Yeah, this is genuinely democratizing access to cutting-edge LLM development. It moves it out of the giant data centers and potentially onto more personal hardware.
Okay, QLoRa is clearly key. What else stands out in terms of optimization?
Oh, another fascinating approach is gradient low-rank projection, or GLOR. This one is somewhat counterintuitive, maybe?
Yeah.
Because it actually allows for full parameter learning, meaning all the model's parameters are technically updated.
Wait, full parameters? How is that efficient?
Right. It sounds contradictory, but it does it in a memory-efficient way. It achieves this by projecting the gradients, the update directions, into a much lower dimensional space during optimization. Imagine you have this incredibly complex error landscape, and you want to find the lowest point. Instead of meticulously mapping every tiny bump and dip, Galore helps you find the most important, directions to move in, the principal components of the gradient.
Ah, okay, so it simplifies the update signal.
Exactly. It simplifies the update signal, making the optimization process much more memory efficient without completely sacrificing the ability to update all parts of the model. It's a different trade-off.
Interesting. And you mentioned DOR earlier, too.
Yes, a DOR, or weight decomposed low-rank adaptation. This method takes another innovative angle. It decomposes the pre-trained weights into two components, magnitude and direction. Then, during fine-tuning, it updates only the directional components, and it does that using low-rank adapters similar to LoRa.
So it isolates direction from magnitude for the update.
Precisely. This distinct approach aims for potentially enhanced performance and maybe better fine-tuning stability compared to standard LoRa. It offers another dimension, another knob to turn in parameter-efficient learning.
Okay, those are incredibly insightful examples of optimizing what gets updated. But what about the other side? Enhancing the underlying computations to make the whole training process faster and less memory hungry. What kind of clever tricks are happening under the hood there?
Right. This side of efficiency is equally critical for practical deployment, and LlamaFactory integrates some really powerful techniques here as well. Flash attention is a prime example. Developed by Tri-Dow and his team at Stanford, this is a hardware-friendly approach. It fundamentally optimizes the input-output, the I/O, costs of the attention mechanism.
The attention bottleneck.
Exactly, the attention bottleneck, especially with long sequences. Instead of constantly moving large chunks of data between different levels of memory, like between the GPU's high bandwidth memory and its on-chip SRAM during attention calculations, flash attention uses algorithms that are specifically aware of this memory hierarchy. They try to keep computations local. This leads to really substantial improvements in attention computation speed and also memory efficiency, especially, as you said, for long sequence lengths where standard attention can just explode in cost. It's like streamlining traffic flow on a memory superhighway.
Makes sense. What else? You mentioned S2 attention.
Yes, so building on that idea of efficient attention, there's S2 attention, which stands for shifted sparse attention. This technique specifically addresses the challenge of extending context lengths in LLMs even further. By employing clever shifted sparse attention patterns, basically, not having every token attend to every other token, but in a structured, sparse way, it significantly diminishes memory usage.
Especially for very long inputs.
Exactly. It's particularly critical when you're fine-tuning models with very long input sequences, where the quadratic memory cost of standard attention quickly becomes prohibitive. Think of it as a smart way to process, say, extremely long documents by focusing attention on the most relevant parts, locally and globally, while still keeping the overall context manageable.
Okay, and one more specific optimization you touched on, unsloth.
Right, unsloth. Now, this isn't a general fine-tuning method itself, like LoRa or Galore. It's more of an acceleration framework. It incorporates the Triton framework, which is NVIDIA's language, for writing highly optimized GPU code to specifically optimize the implementation of the backward propagation step for LoRa layers.
Ah, so it targets the gradient calculation for LoRa.
Precisely. This optimization reduces the number of floating point operations, the FLOPs, during that gradient descent phase for the LoRa adapters. And the result is simply expedited LoRa training. It's like a turbocharger specifically designed for LoRa, making an already efficient method even faster on compatible hardware. And the seamless combination of all these diverse optimization and computation techniques within LlamaFactory is really noteworthy. The paper highlights a very practical reduction in memory footprint, which really illustrates the power of this integration. They mentioned that during standard mixed precision training, a model might consume, say, 18 bytes per parameter, or maybe 8 bytes per parameter in pure half-precision training.
Okay.
LlamaFactory, through its integrated approaches like LoRa, can bring this down to only 0.6 bytes per parameter.
Wow, 0.6. That's a huge drop.
It's a dramatic reduction in memory. And that right there is a key enabler for democratizing LLM fine-tuning. It makes it accessible on hardware that would otherwise be completely insufficient for the task.
Okay, with that solid understanding of the efficiency techniques, let's now dive into the architectural specifics of LlamaFactory itself. Starting with the model loader. This is the component that gets the pre-trained models ready for adaptation, right? It lays the foundation for everything else. What exactly does it do to prepare a model?
Right, the model loader is the first step. It begins with model initialization. It intelligently leverages the auto classes from Hugging Face's Transformers library, things like AutoModel for Causal LM, Auto Tokenizer, to load the pre-trained models and initialize their parameters. There's a clever detail here, too. If the tokenizer's vocabulary size happens to exceed the model's embedding layer capacity, maybe because you added special tokens, it dynamically resizes that layer and initializes the new parameters properly. Ensures consistency.
Handles vocabulary mismatches.
Exactly. Furthermore, to enable context extension, letting the model handle much longer inputs than it was originally trained on, it computes the RoPE scaling factor. RoPE stands for rotary position embeddings. Computing this factor essentially adapts the model's understanding of word positions for these extended contexts, doing it in a way that hopefully doesn't distort its existing knowledge too much. It's a common technique now for longer contexts.
So it's definitely not just loading a model off the shelf. It's intelligently preparing it, configuring it, even adapting its core structure for the task at hand. What about integrating those specific attention mechanisms or optimization strategies we just talked about? Things that actually modify the model's forward pass, like flash attention or S2.
That's precisely what model patching handles. So for instance, to enable S2 attention, which might not be natively supported by the base model code, it applies a monkey patch. This basically replaces the model's standard attention forward computation with the optimized S2 attention mechanism dynamically.
Okay, a bit of code surgery.
A bit of code surgery, yeah, done carefully. In contrast, for flash attention, which as we mentioned has been widely supported natively in Transformers since version 4.34.0, LlamaFactory just utilizes its native class implementation. That ensures optimal performance without needing intrusive code modifications. Much cleaner when possible. There's also a crucial consideration for mixture of experts, or MOE, models, which are becoming increasingly popular for scaling model size efficiently.
Right, like Mixtral.
Exactly, like Mixtral. You want to prevent excessive partitioning of their dynamic expert layers, especially when using optimization strategies like Deep Speed 0 Stage 3, which partitions model states across GPUs. So, to address this, LlamaFactory specifically sets MOE blocks as leaf modules. This tells the optimizer to treat them as indivisible units, maintaining their integrity during distributed training. It's a critical detail for performance and memory when working with these large, sparse models.
And what about working with quantized models? You emphasized how important QLRI is, and quantization in general is becoming super common for efficiency, especially on a consumer hardware. How does the model loader handle these?
Right. That's where model quantization comes in. LlamaFactory provides really robust support here. It can dynamically quantize models to 8 bits or 4 bits using the popular bits and bytes library. This includes support for Cuilori's specific techniques,
Yeah.
like double quantization and the 4-bit normal float representation, NF4, which are critical for achieving those minimal memory footprints we talked about.
Okay.
It also accommodates models that have already been quantized using various post-training quantization or PTQ methods, things like GPTQ, AWQ, AQLM, so you can load those pre-quantized models too. Now, the critical point to remember here, and this is really important for users, you cannot directly fine-tune the quantized weights themselves. The quantization process often makes them non-differentiable or just unstable to update directly.
All right. Frozen base.
Exactly. The base weights remain frozen in their quantized state. So these quantized models are only compatible with adapter-based fine-tuning methods, like LoRa or QLoRa. These methods work because they only modify a small set of newly introduced full-precision parameters, leaving the base quantized weights untouched.
That makes perfect sense. And it leads naturally to how these parameter-efficient adapters are then actually integrated into the models for fine-tuning. How does the model loader connect the efficiency techniques with the model structure?
Correct. The adapter attaching mechanism is designed to be highly automated and intelligent. It automatically identifies the appropriate layers within the pre-trained model architecture where adapters should be attached. It basically traverses the model layers to ensure optimal placement. By default, following the recommendations from the QLoRa paper, low-rank adapters are attached to all linear layers. This generally leads to better convergence and performance compared to only adapting a subset.
Okay, comprehensive adaptation.
Exactly. This whole process leverages the PEFT library parameter-efficient fine-tuning from Hugging Face, which provides an extremely convenient and standardized way to implement various adapter-based methods. Standard LoRa, ArsLoRa, DORA, PISA. They're all supported through PET. And as we touched on earlier, to further accelerate training, the backward computation for these adapter layers can be automatically replaced with Unsloth's optimized version, significantly reducing the FLOPs required for gradient calculation.
Nice performance boost.
Definitely. And for specialized tasks like RLHF, the model loader also dynamically appends a value head layer. This is usually a simple linear layer added on top of the transformer model, designed specifically to map the token representations to scale reward values, enabling that complex preference-based learning.
And finally, ensuring compatibility across different computing hardware, different GPUs, maybe even TPUs or other accelerators with varying capabilities. This can be a real headache for practitioners. How does the loader handle precision?
Yeah, that's precision adaptation. The model loader is smart about handling the floating point precision of the pre-trained models based on the capabilities of the actual computing device being used. For NVIDIA GPUs, for instance, it defaults to using bfloat 16 precision if the compute capability is 8.0 or higher. That's typical for newer architectures like Ampere A100s and Hopper H100s. Otherwise, for older NVIDIA architectures, it uses float 16.
Okay, adapts to the hardware.
Exactly. Similarly, float 16 is used for Ascend NPUs and AMD GPUs, while standard float 32 is the default for non-COD devices, ensuring broad hardware compatibility out of the box. There's also nuance in how trainable parameters are handled. In mixed precision training, all trainable parameters, like adapters or the full model of doing full fine-tuning, are usually kept in float 32. This enhances training stability, which is often crucial for convergence.
Right. Gradients can get unstable in lower precision.
Precisely. Whereas in pure half-precision training, like float 16 or bfloat 16 throughout, trainable parameters are retained in that lower precision format for maximum memory efficiency, accepting a potential stability trade-off. The framework manages these choices intelligently based on the training setup.
Okay, so once the model is loaded, patched, maybe quantized, and adapted, the next crucial step is data preparation. And let's be honest, this is often an overlooked but incredibly time-consuming part of the whole ML pipeline. For anyone who's ever fought with, mismatched column names or obscure JSON formats, the idea of a data worker that just standardizes everything sounds like a dream. How does LlamaFactory's data worker module actually simplify this notoriously messy part?
It really does aim to be that dream. The data worker implements a robust and pretty comprehensive data processing pipeline. It handles dataset loading, aligning structures, merging multiple datasets, and finally pre-processing the data into the format the model expects. Its primary goal, its vital function, is to standardize datasets that come from all sorts of tasks and in all sorts of formats. It turns them into a unified structure. This standardization makes them universally compatible for fine-tuning across all the different models and training approaches supported by the framework. It effectively abstracts away most of those messy, time-consuming details of data ingestion and formatting.
So it handles not just different data sources like files versus Hugging Face Hub, but also those inherently diverse data structures you get from different NLP tasks. Can you give us a concrete example? Like, how does that data description specification actually simplify things for someone trying to adapt, say, a very specific, maybe niche data set they have locally?
Exactly. Let's break that down. For dataset loading, it expertly utilizes the datasets library from Hugging Face. That's a powerful tool. It allows users to seamlessly load remote datasets directly from the hub, just by name, or read local datasets using simple loading scripts, or directly from files like JSON or CSV. This library is great because it significantly reduces memory overhead using memory mapping with Apache Arrow, and it also accelerates sample querying. And crucially, for datasets that are just too large to store locally, which is an increasingly common scenario with web-scale data, the framework provides sophisticated dataset streaming capabilities. This lets it iterate over the data sample by sample or batch by batch without ever needing to download the entire massive dataset to disk first.
Okay, streaming is key for big data. Now, about that data description specification and aligning different structures, how does that work practically?
Right, the dataset aligning part. Imagine you have one dataset for instruction following, maybe with columns named instruction and response. Another dataset might be for dialogue, structured as query and answer. And a third could be something complex like shared GPT format, which uses a conversation history stored as an array of dictionaries, each with role and content.
Yeah, completely different structures.
Totally different. The data worker uses this data description specification, essentially a config file, or arguments, to map all of these disparate structures into a standard unified internal format. This internal format might include common fields like prompt, response, system prompts, tools for function calling, maybe even images for multimodal tasks. Table 3 in the paper actually shows examples of these standardized structures. So for a practitioner with a niche dataset, they don't have to write custom parsing scripts for every single new dataset format they encounter. They just need to map their dataset's columns or structure to the framework standard fields in that specification.
Just define the mapping once.
Exactly. Define the mapping, and the data worker handles the rest. It makes niche datasets immediately compatible with the entire fine-tuning pipeline. It's a huge time saver.
Okay, that's powerful. And what if a user needs to combine multiple data sets? Maybe they want to train on instructions and dialogue data for a more diverse conversational signal. How does it handle merging, especially with streaming?
That's handled by dataset merging. For regular, non-streaming datasets that fit in memory or on disk, the process is pretty straightforward. They're simply concatenated together into one large dataset before shuffling happens during training. Simple enough. However, for streaming datasets, just concatenating them sequentially can be problematic. It hinders effective shuffling across the entire combined corpus, which is really critical for robust learning and avoiding bias. You don't want to see all of dataset A, then all of dataset B.
Yeah, you want them mixed up.
Exactly. So the framework offers intelligent methods to alternately read data from the different streaming sources. It might read a chunk from source 1, then a chunk from source 2, then back to 1, and so on. This effectively maintains data diversity batch by batch and prevents the model from overfitting to one data source before seeing the others, even when dealing with massive data sets that can't be fully loaded or shuffled in memory.
Smart interleaving. And the final step in the data worker pipeline, pre-processing. This is especially vital for text generative models, right? Making sure inputs are formatted correctly for instruction following or chat.
Absolutely. Dataset preprocessing is critical, particularly for chat completion and instruction following models, which rely heavily on specific formatting cues. LlamaFactory comes equipped with dozens of predefined chat templates. These templates correspond to the specific formats expected by different popular models, like Llama 2 Chat, ChatML, Vicuna, etc. The framework automatically selects the correct template based on the model type being fine-tuned. This ensures that prompts, system messages, user turns, and assistant responses are formatted exactly as the model expects, which is highly related to its ability to follow instructions correctly.
Gets the formatting right automatically.
Yes. After the appropriate chat template is applied, the resulting text sequence is then encoded using the model's specific tokenizer. By default, during training, the loss is computed only on the model's generated completions, the response part, disregarding the input prompts. This focuses the optimization purely on improving the generative output quality, which is a common practice. Optionally, users can enable sequence packing. This is particularly useful for generative pre-training objectives or datasets with many short sequences. It combines multiple short sequences into a single longer sequence up to the model's maximum context length, This makes better use of GPU compute, reducing padding and potentially speeding up training time significantly.
Okay, model prepared, data structured and unified. Now the trainer module takes center stage for the actual fine-tuning. This is where the rubber meets the road, so to speak. How does it orchestrate these potentially complex training processes efficiently and flexibly?
Right, the trainer module is responsible for the efficient training itself, and it's designed with that same modularity philosophy we discussed. It integrates those state-of-the-art efficient fine-tuning methods. We covered things like LoRa plus Galore, Batum Optimizer. These can be dynamically plugged in, often just by specifying them in the configuration, effectively replacing default components. This really underscores the framework's flexibility. Critically, these fine-tuning methods, the algorithms themselves, are designed to be independent of the core trainer logic. This ensures they can be easily applied to various tasks, pre-training, SFT, RLHF, DPO, without needing extensive code modifications for each combination. You just select the method and the task.
Mix and match.
Mix and match, exactly. Under the hood, LlamaFactory leverages existing, robust, and widely used trainer classes from the Hugging Face ecosystem. It utilizes the trainer from the Transformers library for standard pre-training and supervised fine-tuning. And it adopts the specialized trainers from the TRL Transformer Reinforcement Learning Library for the more advanced alignment techniques like RLHF using PPO and DPO. It even includes support for using TRL trainers for cutting-edge preference optimization methods that go beyond DPO, such as KTO, Kahneman-Tversky optimization, and ORPO, odds ratio preference optimization.
So it keeps up with the latest alignment research.
It aims to, yes, by leveraging TRL's implementations. Tailored data collators are used to differentiate between these training approaches, ensuring the input batches are formatted correctly for each specific objective, e.g. standard language modeling versus preference pairs. For preference data, specifically, a specialized collator constructs batches containing pairs of examples, typically 2n samples, where n are chosen or preferred examples and n are rejected or dispreferred examples. This specific structure is required for methods like DPO, KPO, and RLHF reward modeling.
You mentioned RLHF earlier, and we talked about how notoriously resource-intensive it is, often needing multiple models loaded simultaneously. You said LlamaFactory has a trick up its sleeve here. How does it make RLHF more accessible, particularly for, say, a researcher trying to do cutting-edge work but maybe only has a single powerful GPU?
This is probably one of the most significant innovations within the trainer module, the model-sharing RLHF. As you said, traditional RLHF training often requires managing and running 4 distinct models concurrently. A policy model, the one being trained, a reference model, usually the initial SFT model kept frozen, a reward model, predicts human preference scores, and often a value model used in PPO to estimate state values.
Yeah, 4 models. That's a lot of VRAM.
It's a ton of VRAM. It typically makes RLHF completely prohibitive to run on single consumer or even prosumer devices. LlamaFactory proposes this novel model sharing approach that enables the entire RLHF training process using no more than one base pre-trained model loaded into memory at any time. It's a brilliant trick for accessibility.
Okay, how does that work?
Concretely, it uses adapters. First, it trains an adapter and a value head layer with an objective function specifically for reward modeling. This allows the single base model equipped with this adapter to compute reward scores.
Okay, reward model via adapter.
Then it initializes another separate pair of adapter and value head. These are then trained using the proximal policy optimization, PPO algorithm, acting as the policy model. The magic happens during the PPO training loop. The framework dynamically switches between these different adapters and value heads using PFFT's set adapter and disable adapter method.
Ah, swapping them on the fly.
Exactly,
Yeah.
swapping them on the fly. This ingenious mechanism allows a single pre-trained model instance in memory to serve at different moments within the training step as the policy model with its adapter active, the value model with its value head active, the reference model with no adapter active, just the base weights, and even the reward model by activating the reward adapter when needed to score generated sequences.
That is clever. Reducing 4 models to 1 plus swappable adapters.
Precisely. It dramatically reduces the memory footprint. The authors state this is the first method they're aware of that supports full RLHF training on typical consumer devices. And that is a significant breakthrough for broader accessibility in research, potentially moving complex alignment techniques out of the exclusive domain of large industrial apps.
That's a huge step forward for democratization. Now, for scenarios where you do have more resources, maybe multiple GPUs or even multiple machines, how does LlamaFactory handle distributed training to fully leverage that available compute power?
Right. For distributed training, the trainers within LlamaFactory can be seamlessly combined with DeepSpeak, which is Microsoft's powerful library for large-scale model training. This allows users to fully exploit the capabilities of multiple computing devices, GPUs, or even TPUs via compatible frameworks, primarily through data parallelism. This means distributing the training data batches across the devices, processing them in parallel, and synchronizing the gradients. Furthermore, to enhance memory efficiency even in distributed settings, users can leverage the DeepSpeed Zero Optimizer family, Zero Stage 1, 2, or 3. Zero enables additional memory consumption reductions via sophisticated techniques like partitioning the optimizer states, gradients, and even the model parameters themselves across the available devices or offloading them to CPU RAM.
So it scales up efficiently too.
Yes, this makes it possible to train models or use batch sizes that would otherwise not fit into the memory of a single GPU, even with efficient adapter-based fine-tuning methods. It supports scaling both up and down the resource spectrum.
Okay, so training is covered extensively. But beyond the core fine-tuning, what essential utilities does LlamaFactory offer to support the full life cycle of an LLM? Because, training is only one piece of the puzzle. You need inference, evaluation.
Absolutely. The framework provides several important utilities for model inference. Firstly, it thoughtfully reuses the same chat templates defined in the Data Worker module when building model inputs for inference. This ensures consistency, making sure the fine-tuned model behaves as expected post-training because it's receiving inputs in the format it was trained on.
Crucial for avoiding format mismatches.
Very crucial. It offers flexible support for sampling model outputs, allowing users to generate text using either the native generation methods in the Transformers library or, significantly, using the highly optimized VLLM inference engine.
Oh, integration with VLLM. That's big for speed.
It is. VLM is known for its high throughput, especially due to techniques like page attention. Both Transformers and VLLM integrations support stream decoding, which allows for generating tokens in real time, useful for interactive applications. Furthermore, building on the VLLM integration, LlamaFactory implements an OpenAI-style API server. This leverages VLLM's asynchronous LLM engine and its page attention mechanism to provide high-throughput, concurrent inference services that mimic the standard OpenAI API interface.
Oh, nice. Makes deployment easier.
Exactly. It significantly simplifies the deployment of fine-tuned LLMs into existing applications or workflows that might already be built around the OpenAI API standard. Provides a familiar and efficient interface for developers.
And for quantitatively assessing the performance of these fine-tuned models, which is absolutely critical for validating effectiveness, comparing methods, and iterating on models. What evaluation tools are built in?
For model evaluation, LlamaFactory includes support for several standardized metrics commonly used for benchmarking LLMs. For multiple-choice question-answering tasks, it supports widely recognized benchmarks such as MMLU, covering a broad range of subjects, CMMLU, a Chinese variant, and CEVAL, another comprehensive Chinese evaluation suite. These help measure knowledge and reasoning abilities.
Okay, standard academic benchmarks.
Yes. And for text generation tasks like summarization or translation, it can automatically calculate robust text similarity scores. It includes support for BLU4, often used for translation, and Rouge, specifically Rouge 1, Rouge 2, and Rouge L, common for summarization. This allows users to precisely measure the quality, fluency, and factual overlap of the outputs generated by their fine-tuned models against reference targets. Having this comprehensive suite of evaluation tools built directly into the framework facilitates thorough post-training analysis without needing to set up and integrate separate complex evaluation pipelines.
All right. Bringing all this immense power and flexibility to users, especially those who might prefer a more visual or low-code approach, is LlamaBoard, the unified web interface. This feels like where that democratization aspect really comes to life, doesn't it? What are its key features that make this advanced framework so accessible, potentially even to non-coders?
Exactly. LlamaBoard, which is built using the Gradio library, is specifically designed for codeless, or at least very low-code, customization of LLM fine-tuning and inference. It truly lowers the barrier to entry for many practitioners who might be intimidated by complex command line arguments or configuration files. Some of its key features include, first, easy configuration. It allows for highly interactive customization of all the fine-tuning arguments directly through the web UI, drop-down menus, sliders, text boxes. It makes setting up an experiment much more visual.
Takes the guesswork out of parameters.
It helps a lot. To simplify the process further, it intelligently provides recommended default values for the majority of parameters, guiding users towards sensible starting points, especially if they're new to a particular technique. And critically, users also get the ability to preview their datasets directly within the interface, This allows for immediate validation of data formatting and content before launching a potentially long and resource-intensive training run. Catches errors early.
That's super useful. What about monitoring?
Yeah, monitorable training. During the actual training process, Llama Board offers real-time visualization of training logs and, importantly, the loss curves. These are updated dynamically within the web UI, offering immediate and valuable insights. Users can monitor and analyze the fine-tuning progress, identify potential issues like divergence or slow convergence, or just track how well the model is learning, all without needing to manually parse raw log files or set up separate monitoring tools like TensorBoard. That live feedback loop is incredibly helpful for iteration.
Absolutely. And evaluation.
Flexible evaluation. The interface supports evaluation in two main ways. First, it allows for automatic evaluation by calculating those text similarity scores, LLEU, on specified datasets, providing quantitative performance metrics right there. Second, it includes an intuitive chat interface for direct human evaluation. This allows users to interactively chat with their fine-tuned model, qualitatively assess its responses, its instruction-following capabilities, its tone, and safety in a more subjective manner, which is crucial for many tasks, especially conversational AI.
Okay, both quantitative and qualitative feedback.
Exactly. And finally, recognizing the global nature of LLM development and application, there's multilingual support. The interface is built with localization files, making it straightforward for the community to contribute translations and integrate new languages. Currently, the paper mentions it supports English, Russian, and Chinese out of the box, significantly expanding its reach to a broader global user base, and hopefully fostering more international collaboration in LLM development and fine-tuning.
Okay, so the paper doesn't just propose this robust and feature-rich framework. It also rigorously evaluates its performance, and that's absolutely crucial for establishing its credibility and usefulness. Let's look at the training efficiency experiments first. How do they actually set up these tests? What models and data did they use to benchmark these different methods?
Right, the empirical validation is key. For the experimental setup focus on efficiency, they chose a specific task: generative pre-training. This involves continuing the training of a pre-trained model on new text data. They selected 3 representative models of different sizes for these tests: Gemma 2B, Llama 2 7B, and the larger Llama 2 13B. The training corpus was a subset of approximately 400,000 tokens extracted from the PubMed dataset, which contains biomedical literature abstracts.
Okay, controlled pre-training task.
Exactly. They then directly compared the performance of several fine-tuning strategies: standard full tuning, updating all parameters; freeze tuning, only updating the last few layers; Galore, standard LoRa, and 4-bit QLoRa. To assess efficiency, they measured 3 key metrics: peak GPU memory consumption in gigabytes GP, training throughput in tokens processed per second, and perplexity, PPL calculated on the training corpus itself. Lower perplexity generally indicates a better fit to the data. The perplexities of the original unfine-tuned pre-trained models served as crucial baselines for comparison.
Can you detail the specific hyperparameters and the hardware used for these efficiency benchmarks? Because those details are critical for anyone trying to reproduce these results or just understand the context of the performance numbers.
Certainly. They used a consistent learning rate of 1E5 or 10.5 and a token batch size of 512 across all the methods being compared. The models were fine-tuned using the 8-bit AtomW optimizer, which itself saves memory compared to the standard 32-bit AtomW, and they used bfloat16 precision for the computations. Activation checkpointing was also enabled globally to further reduce the memory footprint by trading some recomputation time for memory savings.
Okay, standard efficiency practices applied.
Yes. Then, the specific configurations varied by method. For freeze tuning, as mentioned, only the parameters in the last 3 decoder layers were actually trained. For Galore, the rank hyperparameter was set to 128 and the scale factored to 2.0. For both standard LoRa and 4-bit QLoRa, the adapters were attached to all linear layers within the models, using a rank of 128 and an alpha value which scales the LoRa updates of 256. These are pretty standard LoRa QLoRa settings.
Got it. And the hardware?
All experiments were conducted on a single NVIDIA A100 GPU with 40 gigabytes of VRAM. This is a powerful but still relatively common professional GPU, making the results relevant. Importantly, flash attention was enabled across all the experiments to optimize the attention computations uniformly, and the unsloth acceleration library was specifically enabled only for the LoRa and QLoRa experiments as it targets those methods, further boosting their potential throughput.
Okay, clear setup. So what were the key findings from these efficiency tests? The Table 4 summarizes this, right? What did the results actually tell us about the practical benefits and trade-offs of these methods when run through LlamaFactory?
Right. The results presented in Table 4 demonstrated several clear and pretty impactful trends regarding training efficiency. First, memory footprint. Calora consistently, across all three model sizes, exhibited the lowest peak memory usage. For instance, fine-tuning the Llama 27B model with Calora consumed only 7.52 gigabytes of GPU memory.
Wow, only 7.5 gigabytes for a 7B model.
Exactly. Compare that to the 38.72 gigabyte required for full tuning the same model on the same hardware. That's more than a 5x reduction. This substantial difference is directly attributable to Calora's aggressive 4-bit quantization of the base model weights, enabling training on significantly more constrained hardware. As we keep saying, this isn't just a minor optimization, it's often an absolute enabler.
Clearly the memory winner. What about speed, throughput?
In terms of throughput, LoRa, especially when combined with the unsloth optimizations, generally showed higher throughput. It processed more tokens per second compared to the other methods. For Llama 27B again, LoRa achieved 1954.07 tokens per second, noticeably outperforming Galore, which achieved 2083.77 tokens per second in their setup. This indicates LoRa's potential speed advantage, particularly with tools like Unsloth optimizing its specific operations.
Okay, LoRa fastest, Colora most memory efficient. What about perplexity, the quality measure here?
On perplexity, which in this pre-training context is a measure of how well the fine-tuned model predicts the next token in the PubMed data, the results were a bit more nuanced. Galore generally achieved lower perplexity, meaning a better fit, on the larger models, like Llama 213B. This might suggest its full parameter update mechanism, even though projected, is more effective at adapting larger architectures in this scenario.
Interesting.
Conversely, LoRa tended to perform better, achieving lower perplexity, on the smaller models, like Gemma 2B. This might indicate LoRa's parameter-efficient approach hits a sweet spot for adapting smaller models effectively without overfitting or instability.
So trade-offs depending on model size, maybe.
Potentially, yes. And a final, critical practical observation from their experiments. Attempting to full-tune the Llama 213B model resulted in an out-of-memory, OMR, on the A100 40GB GPU.
Couldn't even run it.
Couldn't even run it with standard full fine-tuning. This isn't just about minor gains anymore. It fundamentally underscores the absolute necessity and the proven effectiveness of these efficient fine-tuning methods like LoRa, Calora, and Galore for working with even moderately large LLMs like 13 billion parameters. Without them, this type of training is simply not feasible on common high-end professional hardware, let alone consumer GPUs.
Okay, so efficiency is clearly demonstrated, especially the memory savings with Calora and the speed of LoRa. But beyond just training efficiency, the ultimate measure of a fine-tuning framework is its effectiveness. How well do these fine-tuned models actually perform on specific downstream tasks people care about? How did LlamaFactory's integrated methods perform here?
Right, effectiveness is paramount. For the experimental setup focused on effectiveness, they moved away from pre-training and tested on actual text generation tasks. They created carefully curated, non-overlapping training and test sets. The training sets had 2,000 examples each, and the test sets had 1,000 examples each. These were derived from 3 representative text generation datasets: CNNDM, which is a popular benchmark for news article summarization; XSUM, which is known for more abstractive, single-sentence extreme summarization; and EdGen, a dataset focused on generating advertising copy. So a nice mix of tasks.
Okay, standard generation benchmarks. Which models did they test?
They selected several popular instruction-tune-based models for these experiments, covering a range of architectures and sizes. The list included ChatGLM3SP, AI6B, Llama 2.7B, Mistral 7B, Gemma 7B, Qwen 1.57B, Qwen 2.7B, and the then state-of-the-art open model, Llama 3.8B. A good cross-section.
Good variety. And the methods compared.
These base instruction-tuned models were then further fine-tuned specifically on each task dataset, CNNDM, XSUM, AdGen, following a sequence-to-sequence task paradigm. They compared 4 approaches: full tuning, FT, Galore, standard LoRa, and 4-bit Calora. The primary evaluation metric used was the Rouge score, which measures overlap between the generated text and reference texts. Specifically, they reported the average of Rouge 1, unigram overlap, Rouge 2, biggram overlap, and Rouge L, longest common subsequence overlap, scores calculated on the test set of each task. Crucially, the Rouge scores achieved by the original instruction-tuned models, before task-specific fine-tuning, served as the performance baselines.
Right, to see the improvement from fine-tuning. What about the specific parameters used for these effectiveness experiments? Were they similar to the efficiency tests? Need to ensure a fair comparison.
Good question. The parameters were slightly different, tailored for these instruction-following tasks. They used a learning rate of 1E5 again, but a smaller batch size of 4. common for sequence-to-sequence tasks with potentially longer outputs. The maximum input sequence length was set to 2048 tokens. Similar to before, the models were fine-tuned using the 8-bit Atom W optimizer and bfloat16 precision, and activation checkpointing was enabled. The configurations for the efficient methods were kept consistent. Galore used rank 128 and scale 2.0. Both LoRa and QLoRa used adapters attached to all linear layers, with rank 128 and alpha 256. And all these effectiveness experiments were also conducted on NVIDIA A100 40GB GPUs, providing ample compute for these task-specific fine-tuning runs.
Okay, consistent setup. So what did the results from their Table 5, the one summarizing all those row scores, actually reveal? How did the different fine-tuning methods perform when judged on downstream task quality? Were there any standout performers or maybe unexpected trends this time?
The results presented in Table 5 provided clear insights into the effectiveness of these methods. A really significant finding was that LoRa and QLoRa generally achieved the best performance in most scenarios across the different models and tasks. This strongly validates their effectiveness in adapting LLMs to specific downstream tasks while maintaining or even significantly improving output quality compared to the base instruction-tuned models.
So the efficient methods aren't just saving memory, they're actually working really well.
Exactly. For instance, on the challenging exim summarization task, they showed a Mistral 7B model fine-tuned with LoRa achieved a Ruju score of 30.41. Compare that to its baseline score of only 15.87 before fine-tuning.
Wow, nearly doubled the score.
Yeah, a massive leap in summarization quality, really highlighting what task-specific fine-tuning, even efficient fine-tuning, can achieve on these strong base models. Now, there were a few exceptions, as you might expect. For example, with the ChatGLM 3.6b and Llama 2.7b models on the CNN-D agent datasets, other methods, sometimes even full tuning, FT, slightly edged out LoRa or QLoRa in terms of Ruju score. This suggests there can be task-specific or model-specific nuances, and the optimal method might not always be LoRa QLoRa, although they were very strong overall.
So it's still worth considering the options.
Absolutely. Also, it was noted that Galore was not applicable or didn't converge properly for Gemma 7b and Qwen 7b in these particular experimental setups, possibly due to architectural incompatibilities or optimization challenges. And among the different base models tested, the results showed that Llama 3 8b achieved the best overall performance across the board, which aligns with its general standing at the time. However, models like GeeThix-B and Mistral 7b also demonstrated highly competitive results within their respective size categories, 6b, 7b parameters, reinforcing that LlamaFactory effectively leverages the strong base capabilities of these popular open models.
Okay, so beyond the impressive technical capabilities and the strong empirical validation, what's the broader significance of LlamaFactory? What does it really mean for the open source community and the future trajectory of LLM development? How does it genuinely shift the paradigm for practitioners out there?
I think LlamaFactory plays a really crucial, perhaps even transformative, role in democratizing LLM customization. That's the core theme. By providing this accessible, unified, and efficient platform, it significantly lowers the technical barrier. It allows a much wider range of individuals, from seasoned researchers in academia or industry to students to curious practitioners, maybe even small startups, to explore, adapt, and tailor these powerful language models to their specific needs and domains.
Breaks down the resource wall.
Breaks down the resource wall and the complexity wall. This capability fundamentally contributes to the growth and the vibrancy of the open source AI communities. It fosters innovation at a much broader scale than was previously possible when only large, well-resourced labs could effectively fine-tune these models. Its standing is pretty clear already. You mentioned the GitHub stars, but it's also been recognized by being included in Awesome Transformers, which is Hugging Face's own curated list of significant tools and projects in the ecosystem. That's a huge nod to its role as a representative, maybe even leading, framework for efficient LLM fine-tuning. The authors explicitly state they anticipate practitioners will leverage this framework to build their own beneficial LLMs, hopefully driving societal advancements in various fields. However, they also rightly emphasize the critical importance of responsible use. The paper stipulates that strict adherence to the original model licenses, which often have use restrictions, is mandatory when fine-tuning LLMs with LlamaFactory. This aims to mitigate potential misuse and ensure ethical development and deployment practices are followed.
That's a crucial point. So that brings us to what's next for LlamaFactory itself. The authors lay out a clear roadmap for future development in the paper, indicating a commitment to keeping the framework evolving alongside the rapidly advancing LLM landscape. What are some of those key strategic directions they're planning?
Indeed, the paper outlines several key directions for future work. signaling a strong commitment to continuous synchronization with the latest models, the newest efficient fine-tuning techniques, and emerging needs in the field. First, they plan to expand support significantly by enabling fine-tuning for models that support a wider range of modalities. They specifically mention aiming to support models that handle audio and video inputs or outputs.
Moving beyond text.
Right.
Multimodal.
It's exactly. Moving towards multimodal AI. This opens up really exciting possibilities, allowing the framework to adapt models that can process and generate across different data types, not just text. Think fine-tuning models that understand spoken language or describe video content. Second, their roadmap includes integrating more parallel training strategies. This means going beyond the current deep-speed data parallelism and zero support. They aim to incorporate more advanced techniques like sequence parallelism for handling extremely long sequences by splitting them across devices, and tensor parallelism, splitting the model's layers themselves across devices.
For even bigger models or sequences.
Precisely. These strategies are essential for handling the next generation of even larger models and longer context windows that continue to push the limits of single device or simple data parallel memory. This ensures the framework remains at the forefront of distributed training capabilities. And finally, a very interesting direction. They aim to explore stronger fine-tuning methods, specifically for conversational models. They mentioned looking into techniques like self-play approaches, where models might learn by interacting with themselves or variants of themselves.
Like AlphaGo, but for chatbots.
Kind of analogous, yeah. These advanced techniques could significantly enhance the interactive capabilities, the robustness against adversarial inputs, and perhaps even the safety alignment of fine-tuned chatbots and conversational AI agents. It's about moving beyond basic instruction, following towards more nuanced, engaging, and reliable dialogue.
Okay, so to recap this deep dive, LlamaFactory presents a really compelling, unified framework for the efficient fine-tuning of large language models. Through its meticulously designed modular architecture, the model loader, data worker, trainer, it expertly minimizes dependencies. It provides an integrated, adaptable approach to fine-tune, over 100 LLMs now, using a diverse array of efficient techniques, everything from LoRa and Key-LoRa to Galore, efficient optimizers, and advanced attention mechanisms.
And critically, that LlamaBoard Web UI component removes significant coding barriers, making customized fine-tuning, inference, and evaluation accessible to a much broader spectrum of users, not just hardcore coders. The empirical validation we discussed rigorously demonstrated both the efficiency, those dramatic reductions in memory consumption, improvements in throughput, and the effectiveness on real-world language modeling and text generation tasks. It proves that these efficiency gains don't necessarily come at the cost of performance. Often they perform just as well or better than less efficient methods. This framework truly empowers the community.
Yeah, it really feels like a significant step forward in making these cutting-edge LLM capabilities more accessible, more manageable, and ultimately more democratized, which is crucial for fostering wider innovation. It seems to solve a foundational problem, that friction and resource barrier that has historically limited experimentation for so many people in smaller organizations.
Indeed, it really lowers the barriers significantly. So, given this comprehensive integration of advanced techniques, the strong empirical backing presented in this paper, and the focus on accessibility, what fundamental shifts in LLM development and deployment do you anticipate might arise from the proliferation of platforms like LlamaFactory, these unified, efficient, and accessible fine-tuning platforms? How do you think this will impact the innovation cycle for specialized AI applications moving forward, especially for those maybe operating on constrained resources? And perhaps, what new types of bespoke, highly specialized models might we start seeing emerge now that fine-tuning is becoming easier for more people?